Hello dear classmates, welcome back to the logic simulation chapter. In the previous video, we talked about compiled code simulation. In this video, we are going to introduce an even better simulation technique, the event-driven simulation. The compiled code simulation technique has two problems. First, the gate delay model was not considered by compiled code simulation. Second, the compiled code simulation is oblivious. That means this simulator forgets old results in the previous cycle. This is actually a waste of CPU resource. For example, given this circuit, we apply 0, 0, 0 in the first cycle. So we run the code for the first time. And then in the second cycle, we only change input A to be 1. Because the compiled code simulation forgets all the results in the first cycle, so we will need to rerun all the code for the second cycle. This is actually a waste of CPU time because only signal A changes in the second cycle. So, can we do it in a more efficient way? The event-driven simulation was proposed by Ulrich in 1965. The idea is pretty simple. We evaluate a gate only if there is event at its gate input. In this way, we can save a lot of CPU time. An event is a signal value change at the specific time t, and a gate with its input change are called activated. For example, for this circuit A, we can see there is an event at primary input A. This is a rising transition, and the gate G2 is called activated because we have an event coming in at its gate input. We only need to evaluate one active gate, which is G2, in event-driven simulation. The other three gates are not evaluated again in the second cycle because they are not activated. So, event-driven simulation is typically faster than compiled code simulation. This slide shows a zero-delay event-driven simulation example. In this example, all the gate delay are assumed to be 0. At the beginning, we read in the initial condition of the circuit, and we read in a new input vector. We put active primary input fan-out gate into a queue, which is a first in, first out queue of gates. In this loop, we will execute the events every time we evaluate a gate from the queue. If the output does not change, then we do nothing. If the output does change, then we execute this change and we put gate G's fan-out gates into the queue. We continue in this loop until the queue becomes empty. In this lecture, we will use this notation to denote an event, G, VG plus, which means an event where the gate output G is changing to VG plus. At the beginning, we have two events at primary input where A is rising to 1 and B is also rising to 1. So we put their fan-out gates G1 and G2 into the queue. First, we pop out the first event out of the queue, where is G1. because G1's output does not change, so we don't actually need to execute this event. Then we pop out the next gate out of the queue. G2 is now rising to 1. Because this new value is different from its old value, so we will execute this event. The G2 output is now logic 1, and we put its fanout gate, which is G4, into the queue. Finally, we pop out the last event from the queue, and we execute this falling change at the G4 output. Now, there is no more gate in the queue, so we finish this simulation. Now, it's time for you to work on this quiz. Suppose in the first cycle, the value of A, B, C are 1, 1, and 0. The logic values in the first cycle has been denoted in this picture. Now, given a primary input change at B, please finish this event-driven simulation using this flow chart. Now please pause the video and work on this quiz. Okay, are you finished yet? Given this G1 in the queue, we can see that G1 is changing to 1. So this event will be executed since its new value is different from its old value. And we put two fanout gates, which are G2 and G3, in the queue. Please note that the order of these two gates does not matter. And then we pop out the first G3, where the output of the inverter will be changed to 0. So we execute this event and we put fanout gate G4 into the queue. And then we pop out the next event, which is G2 output changing to 1. And we also push the fanout gate G4 into the queue. Now we pop out the next gate, which is G4, out of the gate. Since at this time G4 inputs are 1, 0, so the output of G4 does not change. So this event is actually not executed. And the same thing here. So finally, we have our simulation result, that is output K is equal to 0. Have you got it correctly? Now let's consider non-zero gate delay in our simulation. Suppose that in this simulation, every gate delay has the same nominal delay, 1 nanosecond. Now we denote our event as G, VG plus at T, which means gate G output will change to a new value VG plus at timestamp T. And our simulation flow will need to be changed slightly. Every time we pop up an event from our queue, if the output does not change, then we do nothing. If the output does change, then we have to execute this event, which means that we update the output of the gate, and we will need to schedule new events in the future into the queue. Please note that the queue is now a priority queue of events sorted by timestamp T. Okay, given the same circuit and the same test pattern, Now let's show this simulation one by one. At timestamp t equal to 0, we have a primary input change at input B, which will schedule an event G1 output to be 1 at time 1, because the gate delay of G1 is 1. Now at timestamp 1, we pop up this event. Because G1 output is different from its old value, so we will execute this event at time 1. This event will schedule 2 more new events where G3 output will become 0 at time 2, and the G2 output will become 1 at time 2. Now at timestamp 2, we execute this event, so now G3 output is 2. When we evaluate gate G4, please note that J is equal to 0, but H is still 0 at this time. So we will schedule a new event at time 3 where G4 output will become 1. Now at timestamp 2, we pop up the next event. So G2 output is now 1. And again, we evaluate G4. At this time, H is equal to 1 and J is equal to 0. So K will become 0 again at time 3. Then at timestamp 3, we pop out the first event out of the queue, and we execute this event at time 3, and then we execute this event at time 3 again. Okay, if you watch this video very carefully, you will find out that at timestamp 3, actually G4 is toggling from 0 to 1 and back to 0. This is what we call a simultaneous signal change. This actually wastes the CPU time without doing anything new. So can we do better? This is an interesting FFT for you to think about. Now let's work on a more complicated example as a quiz. At time 0, A is rising to 1. At time 2, C is falling to 0. At time 4, B is falling to 0. At time 8, A is falling to 0 again. Given these input events, please run the event-driven simulation and fill in this table. First, given these input events and given the delay of each gate, which are different, please fill in the table. Given A is rising to 1 at t equal to 0, we schedule an event where G2 output will be changing to 1 at time 8. At timestamp 2, when C is falling to 0, so we will schedule an event where G2 output will be changing to 1 at time 10, and so on and so forth. Now please pause the video and fill in this blanks. Okay, have you finished yet? Now, at time 14, we execute this event where G4 is changing to 0. At time step 16, we execute these two events, and we will schedule 2 more events. Please note that G4 is having a simultaneous signal change. At time 20, we execute this event, and we will schedule 1 more event. Finally, at time 22, G4 will become 0. This is a long quiz, so please work on this quiz very patiently. Now, if you look at this result very carefully, you will observe a few interesting things. At time 10, when G1 is supposed to rise to 1, but actually signal E is already 1, so there is nothing to rise. Similarly, at time 20, G2 is supposed to be falling to 0, but actually H signal is already 0 at time 20, so there is nothing to change. Again, at time 22, G4 output K is already 0, so actually there is nothing to change. We call this false event, which causes no change in our signal. False event actually does nothing. It's a waste of CPU time. So can we modify our algorithm and remove these false events? Now we show this event-driven algorithm, which takes care of the false event. At the current timestamp T, we check the event. We update the gate value. For every gate J in the fan-out list of gate G, we update the input value of J, and we evaluate the value of J in the future, which is denoted as Vj plus. If Vj plus is different from the last scheduled value, then we schedule this event in the future at time T plus Dj, where Dj means the gate delay of gate J. And we also update the last scheduled value for gate J. If we can do this, then we can avoid a false event to be scheduled. This is a good trade-off of memory for faster speed. Now there is one last thing to be considered. How can we implement this event list? There are 2 possible implementations. The first one is we can use a linked list to implement the event list, where T represents a timestamp. Following each timestamp, we have a linked list of events at timestamp T. This implementation is flexible. We can easily insert a new timestamp. However, if we want to search for a specific timestamp, it would require a sequential search, which is very slow. The second implementation can be a cyclic array, or called timing wheel, which was invented by Ulrich in 1969. In this implementation, we have a circular list where each slot represents a particular timestamp. For each time slot, we have a linked list of events which is supposed to happen at the corresponding timestamp. The advantage of this implementation is that it's fast to search. We can easily access a particular timestamp. But the problem is that delta t of each timestamp is fixed. So we cannot insert an arbitrary time slot between two neighbor time slots. And we have limited L slots in a cycle. Finally, we will sum up our video today. In this video, we talk about event-driven simulation, which consider gate delay in the circuit. This simulation technique is faster than compiled code because we only evaluate gates when events occurred at gate input. We show two algorithms where gate delay is 0 and gate delay is non-zero. We also show that false events are redundant events that can be removed. We show two different event list implementation. Linked list is slow but flexible. Cyclic array is fast, but the time slot is fixed. Now we compare two techniques. The compiled code is simple to implement, but it does not consider gate delay, and it's oblivious. So it may be suitable for high circuit activity. The event-driven simulation considers gate delay. It only simulates the parts of the circuit where events occur. It is suitable for circuits with low activity, but the algorithm is more complicated to implement. In general, event-driven simulation is better simulation technique than compiled code. Before we end this video, we have an interesting FFT for you to think about. Remember, in the previous slide, we show the output of G4 is changing from 0 to 1 and 1 to 0. This is called a simultaneous signal change. Simultaneous signal change actually wastes our CPU time. So can we do better? Here is one idea. This idea is called a two-pass algorithm. In the first pass, we execute the event in the event list LE, and then in the second pass, we evaluate the gate in the activity list so that all the input to a gate will be evaluated here together. In this way, we can avoid simultaneous signal change. Is this a good idea? For idea number 2, we use the same algorithm, but this time we add a last schedule time variable for each gate. when we find that we schedule a simultaneous signal change, we would cancel the previous event so that we will not have simultaneous signal change at the same time. So is this a better idea? Which one of idea 1 and idea 2 is better? Please compare them and tell me what you think. Thank you. Bye bye.